So welcome back, guys, and as ever I do hope you and your family are keeping well. So what we're going to look at today is your third lesson on gravitational fields, and to begin with it's going to be a little bit of a myth buster, and then we're going to look at the gravitational field strength surrounding a single mass. Okay, let's get started with our first myth, I suppose. It's this one. Okay, so there's no gravity in space. Yeah, there can't be any gravity in space because you've seen those astronauts floating around in their spaceship when they orbit the Earth or they go off to the moon. Okay, and there's a lot wrong with what I've just said there. How about this then? What about the moon? It orbits the Earth. So how would the moon manage to orbit the Earth? How would it be kind of held in around the Earth if there was no gravity in space? Okay, so let's have a look at this silly statement. You know something from my previous work about the radial field. Okay, so we looked at masses. And we said that they have a gravitational field around them. And the gravitational field around a mass can be modelled. So maybe if this is the Earth, can be modelled with a series of field lines. And the field lines show the direction that an object would move if it was released. And the closeness of the field lines shows the strength of the field. So remember, if ever you get asked to draw this, really make sure that you use a ruler, I've just sketched it, and that you put the direction of the field on and you make sure it doesn't go inside the object. Remember that we're pretending this is a point mass. So if we were to back off a long way from my picture, it would appear that these things were going to the centre of a dot. Well, look at it. Okay, we've got gravitational field lines out here, and if I continued my diagram, they would be all over the page. So there is a gravitational field due to a single object and due to all the others in space. So it's completely wrong to say there's no gravity in space and the astronauts feel no forces whatsoever, okay, due to gravity, and they wouldn't orbit the Earth if they didn't feel a force of gravity. Moon obviously proving that there must be forces out there, and we looked at that last lesson. We looked at the force between two masses. So let's take this a little bit further, and I want to remind you that G, the gravitational field strength at any point, is at GCSE, and correctly, the force per unit mass. So we can say it's F over M. Now at GCSE we give that a fixed value for on the surface of the Earth, but at A level the force per unit mass varies as we go further away. The mass stays the same, but the force gets weaker due to the field lines spreading out. Okay, and we also know that this is, in sort of SI units, it's the force or the newtons per kilogram. Yep. So we're clear now that the force on any object in a gravitational field will be the gravitational field strength times by the mass. But we have some other information as well, because if we take the Earth, so I'll draw the Earth here, and we put our little test mass above the Earth. So here's our test mass. So we can work out the force on it. So we'll then know the force per kilogram. We also know how far away it is from the centre of the Earth. And we can ask ourselves, therefore, what is G here? Okay, what is G at this point in space. Now, we have to be a little bit careful, okay, because we assume that this is a point mass. So in exams, they often say the object is so far above the Earth's surface, but you must never forget, of course, that that's not the distance that we deal with. Okay, we've got two distances here, and we have to be really clear in our minds that we've got this distance, okay, I suppose correctly from the centre of mass of the object, so that's the sort of height that it's orbiting, and we've also got this distance from the centre of the Earth down here. So when we do any maths on this, the distance that our object is away from the mass is always from the centre of the mass. So don't forget that if this is the Earth, that when you do your calculation, you've got to add the radius of the Earth to the height that it's at. I'll just put h there, okay? I suppose this is an altitude, really. So that the r that you use in equations is the radius of the Earth plus the orbital height, okay? So the r that you use will be equal to the radius of the Earth plus the height that it's at. And that's really, really important, because it's so easy in exams when they say the object orbits 200 kilometres up. Firstly, to make the mistake that you're in kilometres and you must be in metres, and secondly, to put 200 into your equation. But it's not, it's that distance plus that one. I know I'm labouring that point, but it comes up again and again. Okay, so let's just take this a tiny bit further. Now we've got an understanding of what the distance is, and we remember something from previous lessons. So this is what I hoped you'd remembered from a previous lesson. So we know that the gravitational field strength at any point is the force per unit mass. Okay, so I'm going to put a little m there. And remember that that's the force acting on the test mass. Okay, so this is the object being pulled in the gravitational field that we're interested in. Not the Earth, if you see what I mean, not the large mass. Okay, or at least it's easier to think about it in that way. But I hope you remember that also the force between masses, it was Newton's law of gravitation, was equal to minus g m1, that's the mass of the Earth, m2, or little m, the mass of the object that's being pulled in, divided by their separation squared. Okay, and because there's lots of m's in this, it can get very confusing, but I've made sure that I've drawn it in a different colour. So look what happens, and I really like this. We won't worry too much about the vector nature at this stage. We'll just talk about the magnitude. But look what happens if we divide this side by m and divide that side by m. So we bring m over here. So we've now got that the force per unit mass, because we've moved the m to here, which is g, which will be g m upon r squared. Okay, so what we've done here is we've shown that the gravitational field strength at any point away from a large point mass, or any point mass in fact, will be equal to big G, the gravitational constant, multiplied by that mass, divided by the distance you are away from the centre of it. So we've kind of derived an equation here to show what the gravitational field strength is at any point away from a mass, and of course there's your over r squared. It's a radial field separating in those two ways. So that's going to be a very useful equation, and I'm going to show you some of the calculations we can do with this. So, well done on that, and you'll notice from this that the gravitational field strength, G, is proportional to M, but it's inversely proportional to the distance from the centre of mass squared. And that's an interesting point to note, coming from Newton's law of gravitation. Now, I'd like to take this just a little bit further and show you this graphically. Okay, so to do that, I really need to put the minus back in there just to get the vector nature of this, because the graphs you'll see at A level should be drawn correctly. So let's have a look at this graphically. And this is an important skill to be able to interpret these sorts of equations graphically. So if we were to measure G at different distances away from a point mass, okay, remember that the vector nature is in the opposite direction, and we drew a graph of what G is as we go further and further away. So here we go. There we are, going further and further away, and this is going to be the value of G. Okay, and I'm making the point that it's a negative value because the field line goes towards the object. It's an attractive field, and we are backing away from it. So this graph will be an inverse square. Okay, so you could call this straightening the graph, but it's a really important technique at A level to be able to get a straight line from data like this. Well, we know that G is proportional to 1 over R squared. So if we draw a graph of G against 1 over R squared, we should get a straight line. So here we go. Just get the axes in place. So here's our value of G. Negative again, remember. And if we take every value of 1 over R squared, you'll notice that G is equal to a constant 1 over R squared, so it will give a straight line. So there's our straight line. I kind of purposefully, as a teacher, those of you that know me, don't draw these lines at 45 degrees because there seems to be an obsession that every straight line graph must be at 45-degree angle. Okay, and of course it doesn't have to be. It depends on the scaling of the numbers on the axes. Okay, now let's work out the gradient of this line, and you've kind of really got to pay attention here because the letters we use are a little bit confusing. So I'm going to pick a black pen and come up here. So the gradient of the line will be the change in y over change in x. Okay, so the gradient will be g over 1 over r squared, which all looks a bit weird. But another way of looking at it is to say, do you remember that y is equal to mx plus c? Right, okay, now, bit of a fiddle. That m is the gradient of the line. Okay, so please don't think that's a mass. That is this funny value that I've drawn here. Okay, but we also know something else. We know that c must be 0 because it goes through 0, 0, so it doesn't cross the y-axis at any other value, and that y here is g. This is the y-axis. Okay, so if I write it like this, g is equal to minus gm multiplied by 1 over r squared. So I hope you agree that this is just g equals minus big G m upon r squared. Have a really close look at that. Y equals m, there's our x value, plus c, and there's no plus c. So what comes out of this is that this m here, which is the gradient, is equal to minus g big M. So that's a way of using graphs, and you could be asked to do something like this at A level. So it's good to show that you understand how to straighten a graph, as it were, and then you use y equals mx plus c, and you look at the equation you've got, and you pull out the x value, you pull out the y value, there's no plus c, so this bit here must be the gradient of this graph. Now, I'll just end by saying that's quite interesting, because if you know the value of big G, then this will allow you to calculate the mass of the gravitational body that is creating this gravitational field. Okay, so let's head off to the moon now. And this is going to be a little bit more complicated, because if we go off to the moon, we aren't just moving away from the Earth, we're also moving towards the moon, which has its own gravitational attraction. So if you think that through, you're kind of being hauled back to Earth, and it's getting weaker and weaker and weaker as you go away, and you're getting pulled towards the moon more and more and more as you get closer. But the two masses aren't the same. Forget the sizes, it's not about the sizes, remember they're point masses, and they could be similar sizes but different densities. The crucial thing is that the pull from the Earth, okay, when you're going to be between the Earth and the moon, an equal distance, the pull from the Earth is going to be stronger because it has a stronger gravitational field, because it's more massive. So, how can we graph that? Well, I have to think carefully about how to draw this one and get it right. So, the graph of how the gravitational field varies as we are astronauts and move away from the Earth looks something like this. So, I'll just get my axes in place. And this one, as ever, is going to be r. And that r is the separation, the distance from the centre of the Earth. And this axis is going to be g, okay? And I won't give units to r because I'm not worried about the specific distances, but remember that g will be in newtons per kilogram. So it's here we've got to be a little bit careful, because I'm going to draw a sort of little picture of the Earth. So that's the Earth. And there's the centre of the Earth, okay? And the reason I've done that is, remember, as astronauts, we don't start here, we start here. We already are at a distance away from the centre of the Earth before we even get going at Cape Canaveral, okay? So, this point here is the radius of the Earth, and that's where we're going to begin our journey from, okay? But we know something. So if I come to here, okay, we know that on the Earth's surface, the gravitational field strength is minus 9.81 newtons per kilogram. Sorry, not a very well drawn graph. So there we go. So we know that at this distance on the Earth's surface, that's the gravitational field strength. Okay, and we're going to travel away and away and away. It doesn't really matter whether you orbit the Earth and do all those sorts of things to get to the moon. The main thing is, how far away are you from the centre of the Earth? Okay, well, I'll put the moon here. So there's moon, okay, and there's the centre of the moon. And as astronauts, let's not forget that we are going to travel from this point to this point. We're not going to bore into the centre of the moon and go inside it. Okay. Now, this is a little bit more complicated because you want to draw this sort of curve like this, yeah, the inverse square. But remember that the gravitational field due to the Earth gets weaker, but then the moon starts to pull you. So we've got to combine the two. Now, it's not going to be absolutely brilliant, this drawing, but I'll try my best. Okay. We get a sort of graph that is going to be positive when we get to the moon. Okay, so it's positive, and then it's going to curve away, and then this sort of a shape. Okay, so I've done my best there. It's not exactly perfect. You could write a computer program and actually draw this properly. But what do we note? As we go away from the Earth, the gravitational field strength gets smaller and smaller and smaller and smaller. Okay. As we are very close to the moon, it gets larger and larger and larger. And obviously, it's not going vertical there. But it has a point, okay, here. And the value of G on the moon is about plus, or compared to the Earth, 1.6 newtons per kilogram. Okay. So a kind of positive value with reference to the Earth if we're measuring, this way. Okay, right, now, what comes from that? Well, the thing that's really interesting you'll notice from this graph is this one little point here. Okay, here, G equals 0. So, if you imagine it, there's a place between the Earth and the moon where the Earth is hauling you back home, okay, and the moon is pulling you the other way. And if you add those two vectors, you get to a point where you're neither, in total, sum of forces, being pulled either way. And at that point, you will feel no newtons per kilogram. The gravitational field strength will be 0. I'm not even going to begin to try and draw that kind of concept with gravitational field lines, but we can show it quite nicely graphically. Okay, there are lots of these places in the solar system. You've got to imagine a point between the sun and the Earth where the gravitational field strengths cancel out. And there are many, many more. They tend to go under the term Lagrangian points. And I always ask people, what happens if you were to kind of open the door of your spaceship at this Lagrangian point and put an astronaut outside in all their kit, close the door and chase off? Okay. Well, if you think about it, and I'm going to get this slightly wrong to begin with, if you think about it, if you left an astronaut there stationary and they didn't have any kind of power pack, jet pack or what have you, they're going to be stuck there forever. Okay. They're not going to be hauled towards the Earth or pulled into the moon. They're going to be stuck. It's kind of a place where you can park stuff. What's very wrong with what I've just said is, of course, remember that the moon is moving, or at least the two masses are moving with respect to each other. Okay, so this point here will not remain at the same coordinates in space. Okay, so time for a bit of a calculation. Now we know a bit more about gravitational field strength away from a large point mass. So, my title is Dogs in Space. And those of you who know my other YouTube work and are taught by me in the classroom will know that Laika lives here. And Laika spends all of her time travelling, not orbiting the Earth as such, but orbiting on its surface, travelling around the world with my students. So we're going to look a little bit at what Laika did back on the 3rd of November, back in 1957. So she was an astronaut, or in fact, she wasn't an astronaut, she was a cosmonaut because she came from Russia. And they wanted to find out how animals behaved in space, ready for sending humans up there. So Laika was popped into Sputnik 2, Mutnik as some people nicknamed it, I think the Americans. and she was sent flying up into space. And what I thought we'd do is have a look at what her weight was, in other words, using the gravitational field strength of her orbit to try and find out how heavy she felt as a cosmonaut dog. So we've got this sort of arrangement. So here was the Earth. Where's the Earth? And Laika, I'm not even going to begin to try and draw a dog, but there's Sputnik 2, okay, and Laika's strapped into that, so Sputnik 1, 2, there it is, okay, blasted up into space. I suppose it had CCCP written on it, okay, and I'd like to see if we can do some calculations. Okay, the first thing I'd like to do is to give you a little bit of data about Laika and where she ended up in space. The end of the story is a bit of a sad one, and I'm going to leave you to Google that if you don't know what happened, and in some ways what a dreadful PR stunt it was for the Russians at the time. But let's have a look at little Laika. So Laika the dog was, as near as we got, 5 kilograms in mass. Okay. The Earth was the mass that she moved away from, and the mass of the Earth is a very large number, 6 times 10 to the 24 kilograms. Okay. And the Earth has a radius, so the radius of the Earth is, watch me here, 6,370 kilometres. So, I know I'm going to bang on and on about this, and you're probably tired of it. Okay, wrong units. Let's get that in metres. And secondly, this one, remember that wherever Laika is, she must be at least this one this far away from the Earth, okay, because you always measure from the centre of the mass. So we've got some data there, so what we need now is some questions. So the first question I'm going to ask is, if we put Laika in orbit, well, the orbit that she took was somewhat complicated and didn't quite go as planned, and it was not a circular orbit. Okay, she ended up in an elliptical orbit, and we'll do a little bit more work on those later on. But what I'd like you to imagine is that the orbit is kind of egg-shaped, and it has a very close position towards the Earth, and then much further away. Okay, it has a perigee close to the Earth and an apogee, the highest point. Okay, and I want to know some data about her at the highest point of her orbit. Okay, so the apogee, interesting word, of Laika's orbit above the Earth, okay, was 1,700 kilometres. Okay, don't forget that this is above Earth. Okay, so the questions. So my first question to you is, number one, when she was at apogee, so when she was at the highest point away from the Earth's surface, what was her mass? So Laika's mass at that point. Okay. The second question I want to ask was, at the apogee, what was Laika's weight? And the third thing I want to know, okay, is, using that, can you make sure that you write down G, yeah, the value of G at Laika's apogee? So if you got asked any other questions, like some other objects in the Sputnik 2, what weight do they feel? So can you pause the video now, okay, and hopefully, if I've been any good at this today, use the physics that I've taught you to work out what her mass will be up there, what her weight will be up there, and please state for the record what the value of G is at this point above the Earth's surface. Okay, so pause there, do your calculation, and we'll have a look at your answer in a moment or two. Okay, so let's see how you got on. So, firstly, the first question is a really easy one to answer. Mass is a measure of the number of atoms in an object, the amount of material. And Leica's Leica, she's a 5 kilogram Leica, and that's the answer, obviously. So that was an easy one. Yeah, Leica's mass is 5 kilograms. That hasn't changed. Okay, I know one or two of you will know about general relativity and all of that sort of business, but look, you know, it's going to be 5 kilograms up at that apogee point, whatever happens. Okay. However, the gravitational field's weaker, so her weight is going to be lower. And if we know the value of G, we can work out her weight, and we can work out what kind of percentage it is of her weight on Earth. So here we go. Just wind on a little bit here. So there's our data. So I hope what you did was you straight away reached for the equation that we've done. So G, the gravitational field strength, at any distance away from the centre, I'm labouring it yet again, of a point mass, is minus G, the gravitational constant, M, the mass of the object that we're moving away from, the large mass, divided by our distance from the centre of that mass squared. Okay, so I think the numbers are going to get a little bit tiny when I write them on here, but I'll try my best. So G, the gravitational field strength, is big G, 6.67, making that point very clear, times 10 to the minus 11, okay, times by, now we've got the mass of the Earth, and it is in kilograms, so 6 times 10 to the 24, okay, all divided by, now it's here you really need to switch on, because it's the first time you've seen this. Okay, we are above the Earth's centre, on the surface of the Earth, and then out in space. So how far are we away from the centre of the Earth? We've gone from the centre of the Earth to the surface, to the apogee of the orbit. So we've got to add those two distances. So the radius of the Earth is 6,370 kilometres times 10 to the 3 metres. And then she goes up even higher to 1,700 kilometres. Okay, so that's your first mistake at A-level. You'll forget to put in the radius of the Earth. And then the next mistake you'll make, and I make it time and time again, is squared. Okay, so we've got to square that. Now, again, we've discussed calculators before. You're on your own here, okay? Do what you do with your calculator. I have a very old calculator, and I do that and put it in memory and all sorts of things. But be really careful that you're not just sticking in the numbers and pressing equals and being happy with what you've got. Look at your answer and work out if it's sensible. Okay, so G comes out pretty much equal to 6 newtons per kilogram. Okay, so we've got this one. We've got the value of G at her apogee, the highest point in the orbit. Okay, and we know that her weight, so Leica's weight, yep, W will be equal to mg. Okay, so if we do that, her weight will be m, which was her 5 kilos, times g, which is 6 at that point. So her weight will be 30 newtons. Okay, so we can say here we've got Leica's weight as 30 newtons. because we know the gravitational field strength at this point was 6 newtons per kilogram. And I'm not going absolutely mad with significant figures here, but units, guys, make sure you always put the units on things. Otherwise, we don't know, is it in kilometres, is it in metres, and what have you. Okay, so she was on Earth about 50 newtons. She's now 30 newtons, so she's approximately 60% of her Earth weight. Yeah, I think I'll write that down, of the Earth weight. So, what have we shown there? Well, we've revised our equation and all the little traps we can fall into when doing it. But most importantly, this point here, that if you're an astronaut or a cosmonaut dog and you're up in space, you are not weightless. In other words, you do not have zero weight. There is a force on your mass, okay? But perhaps to end on this, remember that when you see astronauts apparently weightless, they're falling, accelerating downwards, and their spaceship is accelerating down at the same rate. So they're not catching it up. So a photograph of that or a film of that makes it look as if they're somehow hovering or floating around. I don't like either of those terms. There's no floating going on. They're actually in free fall. Okay, so I do hope you enjoyed that lesson and found it useful, and you've now got a better understanding of gravitational field strength and how to calculate it. I'll be doing another lesson on gravitational fields soon, and I look forward to seeing you then.